Great. So yeah, thank you for the introduction. Today, as Aleph says, and as you all know, I'll be talking about RUMBA, which is a spherical deconvolution local reconstruction algorithm. I will go through what RUMBA is and how you can use it in its new implementation in Dipy 1.5.0. As a heads up, I tested positive for COVID yesterday, and so I feel fine, but I might pause a couple of times to blow my nose, but it should run generally smoothly. Okay, so we will start from the basics. So spherical deconvolution, this is something I'm sure you are all, for the most part, familiar with. This is an approach to local reconstruction where we can frame our diffusion-weighted signal as being the result of a convolution between some single fiber response function and our fiber orientation density function, our FODF. Now in local reconstruction, we want to move from the signal to the FODF, and so this amounts to solving this deconvolution between the signal and the response function. There are generally actually two main ways of framing this spherical deconvolution approach. There is this convolution-deconvolution construction. And when you solve this deconvolution, you get a continuous fiber orientation density function as your result. You can also expand this single fiber response function into a dictionary of rotated single fiber response functions. It looks something like this, choosing some finite set of points along a sphere. And this essentially discretizes the problem. And if you solve this inverse problem, you get a discrete FODF along this finite set of directions. So both of these approaches get at the same thing. Generally, you do this deconvolution approach when you're working with spherical harmonics, because then convolution becomes multiplication in the spherical harmonic domain, or you can work directly with this inverse problem. And this is what RUMBA does. So RUMBA is one of these dictionary-based spherical deconvolution methods that solves this ill-determined, ill-posed inverse problem. Now, I will get into how RUMBA actually solves this problem in more detail later, but to arrive at that point, we first have to have a discussion about noise in MRI data and the form that noise takes. So this is a high-level schematic of how the final magnitude images that we work with are constructed in your MRI scanners. To begin, at each coil, they acquire some estimation of the real image. At this point, the signal is complex, and it is affected by correlated complex Gaussian noise. Next, we combine these complex signals from each coil to yield our final magnitude image. And this can be done in one of two primary ways. There's the spatial matched filter approach, or SMF, and there's the root of sum of squares approach, or SOS. And in both cases, the complex signals undergo some sort of nonlinear transformation to get the final magnitude image, and the noise distribution is transformed from being Gaussian to something else. Specifically, in the spatial matched filter approach, initially the complex signals are combined linearly, and at this point the noise remains Gaussian. But then we take the magnitude of this combination, and magnitude is a nonlinear operation. The magnitude of a Gaussian is a Rissian distribution, and that's what we end up with. In the roots of sum of squares approach, you take the root of the sum of squares of these complex signals, and this itself is nonlinear, and this results in a non-central chi noise distribution. If you are unsure of what type of scanner you have, generally they are this spatial matched filter type of scanner, and so that's the more reliable assumption we can make. So what do these distributions look like? This is an example of real diffusionmri data constructed with 32 coils. On the left, it was following the sum of squares approach, and you get this non-central chi distribution on the bottom. On the right, it was using the spatial matched filter approach, and you get this Rissian distribution on the bottom there. And just from looking at these histograms, there are a couple key observations we can make. One, they both have non-zero means, and two, both distributions are asymmetric. So non-zero mean and asymmetric. Now, the reason why I'm going into detail on the form of noise in MRI data is because aside from two previous spherical deconvolution methods, which did explicitly consider Rissian noise in their local reconstruction method, most previous spherical deconvolution methods, and the ones that most people use, did not explicitly model the Rissian and non-central Chi signal-dependent bias. In fact, they typically assume that the noise follows a zero mean normal distribution. And we just went over the fact that the distributions have a non-zero mean and they're asymmetric. So you can see where there's a bit of a mismatch between assumptions and reality. And this brings us to the primary property of RUMBA. So I haven't said what RUMBA stands for yet, but it stands for robust and unbiased model-based spherical deconvolution. And there are two adjectives here that I'll go through and justify: robust and unbiased. The first of these is unbiased. And the reason why we can call RUMBA unbiased is because it explicitly uses these Rissian and non-central Chi likelihood expressions in its signal estimation, in its FODF estimation process. So these are the Rissian and non-central Chi likelihood formulas in the context of MRI signals. They are these likelihood expressions for your measured magnitude signal given your true magnitude and the variance of the complex signals at the coils originally. If you compare these two expressions, they are very similar. The only difference is that in the non-central Chi case, it's also parameterized by the number of coils, and a couple of the expressions change, but you'll find that when you sub in n equals 1 in this expression, it actually reduces to the Rissian likelihood case. So essentially, this non-central Chi likelihood expression is our generalized likelihood model for the MRI signals that we can use, and it accounts for all cases of Rissian or non-central Chi noise within it. One term I haven't gone over yet is this I function. This is the modified Bessel function of the first kind. The order is that subscript n-1, and here I've just shown what this function looks like for different orders to get some intuition. But yeah, so this is the core likelihood model that RUMBA uses and that it's trying to optimize. If we were building a cost function that we wanted to optimize, we could imagine encoding this likelihood like this, where we take the negative log likelihood summed over all voxels, and we're trying to find the FODF that minimizes this cost function and thus maximizes the likelihood. Okay. So that was the unbiased adjective. The other one is robust. And the reason why we can call RUMBA robust is because RUMBA uses something called total variation spatial regularization. This is a technique that has its roots in image denoising, as shown here. And the general idea is that it constrains some optimization problem by penalizing the absolute signal gradient across the entire signal, or across the entire image in this case. This has the effect of identifying patches of coherent intensity and getting rid of this local variation while still preserving edges. So mathematically, that might look something like this. So f is the function we're trying to optimize. The vector y here could represent our denoised image in some way. You would have this objective, which in image denoising could mean constraining our denoised image to be globally similar to our original image in some way. And then we add on this total variation regularization term. So we have this regularization strength parameter alpha multiplied by the total variation. And the total variation in the case of images would be something like this. So as I said, summing these absolute signal gradients. In images, you'd be summing over all pixels, over all dimensions, which would be color channels. You can imagine an RGB image, for example, and then taking the absolute value of these 2D gradients, the magnitude of these 2D gradients, and summing them all together. So we can apply this concept directly to local reconstruction. Rather than penalizing our image intensity gradients, we would be penalizing our FODF gradient across the entire brain. And once again, this tries to promote spatial continuity while preserving edges. So rather than promoting continuity in these patches of image intensity, it'd be promoting continuous streamlines like the curvy streamline I have shown here. And ultimately, this reduces noise in our FODF estimation. So the math is pretty similar as in the image denoising case. Rather than summing over pixels, we would be summing over voxels to compute the total variation. The dimension D in this case are the dimensions of our FODF, so all those directions on the sphere in our dictionary, if you remember from the beginning. And because we're working in a brane volume, we're taking 3D gradients, not 2D gradients, but the principle is very similar. All right, so now we can bring together these adjectives, robust and unbiased. This was where we left off our cost function that we wanted to optimize. We can now add on this total variation term. So it's the same thing you just saw on the last page. We have this regularization strength parameter alpha, and we're summing over all of our voxels x, y, z, and over all of our dimensions j to get our total variation. And we have this additive cost function, which if we optimize, we can say we're doing some robust and unbiased optimization of the FODF. In order to actually optimize this expression, we don't use this directly. We don't perform gradient descent. Rather, we encode this in this multiplicative iterative estimation framework. This is something that's used in Richardson-Lucy deconvolution. And so rather than having these additive terms, we are using this multiplicative operation to iterate on our voxels FODF, F here, which gets multiplied by some likelihood expression and some total variation expression. If we were to use all of the formulas I've shown throughout this talk, we could arrive at this construction for this multiplicative scheme. So the likelihood expression becomes this. And these are all symbols that we've seen already. So H is our dictionary from the beginning. S is our measured signal. I is that Bessel function. Sigma is our variance of the noise. And we're just putting them together in this new way as we're adjusting to this multiplicative framework. The total variation term becomes this RK expression, which can be described as such, where we're taking the divergence of our normalized gradients rather than just taking the magnitude directly. And so to understand where these terms are coming from, I would invite you to check out Erick's 2015 paper that introduces RUMBA. But essentially, this is the mathematical machinery that drives RUMBA. This is what's going on under the hood when you are using RUMBA in DiPy. If you look at the code, these are the NumPy operations you will find. Some additional properties of RUMBA. So one advantage of using this dictionary approach is that it's very easy to extend the algorithm to account for partial volume effects. So contributions from things like gray matter and cerebrospinal fluid, these isotropic compartments. All you have to do is add in a couple more columns to your dictionary, a few more dimensions to your FODF F, which correspond to gray matter and CSF. Since these are isotropic, their response functions are just spheres, whose radii correspond to the diffusivity of gray matter or CSF. And so RUMBA has this property built in, so it can estimate the volume fractions of gray matter and CSF alongside the FODF. One warning I have here in red, which I will make sure to emphasize throughout this talk, is that distinguishing the gray matter and CSF compartments is only possible when you're working with multi-shell data. You'll see that when you have single shell data, you can't actually distinguish the contributions of both isotropic compartments. You have to combine them. And I'll show that in more detail later. But RUMBA is very flexible. It's compatible with single shell and multi-shell data. It is compatible with spherical and Cartesian acquisition schemes. So we hope it can serve you in a variety of different research questions. It's also a good method. So it's, at least empirically, it's won multiple local reconstruction challenges in past. This includes Mikai Iron Tract 2019, amongst others. And so we are very excited that it's now available for public use in DiPy 1.5.0. some water. So in Dipy, Rumba comes in the form of two classes, which have been added to the reconst.rumba module. There's the RUMBA-SD Model class. This is what you'll primarily interact with. And this is what you parameterize with all this information about the response and your data and the optimization, and where you call the fit method. The Rumba fit is a class, an object that you use to access the different, all the information provided by the fit, so the FODF and your various volume fractions. And I will go through these class diagrams systematically to make sure that we all understand all of the parameters, all of the attributes in both objects. I'll begin with this RUMBA-SD Model class object or class diagram. So it has 12 attributes, but these are all parameters that you pass to the constructor. So it's important that you understand the influence that each of these have. I've grouped them in some functional way based on parameters that are responsible for describing the data, for constructing your dictionary, your response, and for conducting the optimization. And I'll go through them in these groups. So to start, we have our data parameters. So firstly, it asks for the gradient table of your data. This is a gradient table object in Dipy. It then asks for the reconstruction type. So this is the reconstruction approach used by your MRI scanner. This is either that spatial matched filter approach, which I touched on earlier, or the sum of squares approach, which I also touched on earlier. So this involves looking at what type of MRI scanner you're working with. If you don't know, then once again, using SMF is the more reliable assumption, and that's the default value in the Rumba constructor. Next is the number of coils. So you'll remember that this is a parameter in the non-central chi likelihood formulation. So it's important to know. One thing though, as you remember in the Rissian likelihood, number of coils was not one of the parameters. And so this parameter is ignored if you have an SMF reconstruction type, and you can just leave it at the default value, which is 1. The last thing we need to know about your data is whether it's accelerated or not. So we asked for this acceleration factor R. This is not something I touched on in the discussion about noise, but essentially if your data is accelerated, then this can mean it has spatially varying noise. And so we try to account for that in the optimization. The acceleration factor has different names depending on your MRI maker. So look out for terms like IPAT, asset, or sense when you're trying to identify this. The next group of parameters are those related to the response. So the construction of this dictionary, these rotated disks and those spheres at the end. To begin, we'll focus on these rotated disks, which are the rotated white matter responses. Rumba lets you pass a white matter response in one of 2 ways. So one, you can pass the eigenvalues for a single fiber tensor, or you can pass this spherical harmonic representation of a data-driven, data average response. And I'll go through how you can get to each of these responses. There are methods in Dipy for extracting them. But essentially, your tensor eigenvalues will come in the form of a 3-dimensional vector, an NumPy array, and the data-driven response comes as this axial symmetric spherical harmonic response object, which once again, I'll show you how to get to that. We also ask you to pass a sphere. So this is the sphere on which your FODF is reconstructed. This is the sphere that determines which direction these disks are rotated in your dictionary. This is an important parameter. This essentially determines the resolution of the FODF that you achieve after fitting. So if you have constraints in that regard, it's important to choose your sphere carefully. You can pass a sphere or a hemisphere object in Dipy. It's advised to pass a hemisphere object generally because Rumba, the FODS provided are symmetric. And so you can just get the same information, but twice as fast if you pass a hemisphere. The last 2 parameters for the response section are the gray matter and cerebrospinal fluid responses. These are just floats which correspond to the gray matter or CSF diffusivity. and these generate these spherical responses in our dictionary. You can pass none to these parameters as well, and that will ignore, that will not compute these additional compartments if that's not something you're interested in accounting for. And once again, I have this warning in red. Distinguishing these compartments is only possible when you have multi-shell data, right? So when you have single shell data, generally you can just pass the gray matter response as none, for example, and just treat your CSF compartment as your general isotropic compartment. But to get a sense of what this looks like, I ran this little experiment. So this is running Roomba on in vivo data. Specifically, it's the Sherbrooke 3-shell data sets in Dipy. You can see that when you just use one shell of this data sets, the gray matter compartment, you get nothing, you get no information, and the CSF compartment seems to include all of the isotropic volume fractions combined. All right, so when you have one shell, you cannot differentiate between gray matter and CSF. You can't treat these compartments as being volume fractions directly of gray matter or CSF. You only get one general isotropic compartment. But when you have more than one shell, so 2 shells or 3 shells, we see the separation between the gray matter and CSF compartments. And at this point, you can start making some judgments about the gray matter volume fractions that actually correspond to gray matter behavior in the brain. The last set of parameters are our optimization parameters. So the first 2 are pretty straightforward. There's the number of iterations, so the number of multiplications in that iterative scheme I showed earlier. This defaults to 600. This is generally a good starting point. This is a number that we've used, or that Erick has used in past local reconstruction challenges that has won them. And so it generally reflects the amount of optimization necessary to get good FODFs in Roomba. There's also this verbose parameter, which just determines whether you log updates on iteration progress or not. These last 2 are very important, so I'll go through them carefully. The first is this voxel-wise parameter. So essentially, this determines whether you compute your FODFs voxel-wise, so computing each FODF for each voxel sequentially, independently, or globally, where you compute the FODFs for all voxels simultaneously together. So if you set this parameter to false, then you're in this global fitting regime. And what this means is, because you're fitting all the voxels simultaneously, you have to be able to fit your entire data set into memory. And this can definitely be a constraint depending on the machine you're working with. But if it's possible, then this vectorizes your computations and speeds them up a bit. It also allows for total variation regularization. So total variation is only possible when you're in this global fitting regime, because if you remember, we needed information about the entire brain volume to compute total variation. We need info about neighboring voxels to compute gradients. And so it's only possible when you're fitting the entire data set into memory and computing the fit globally. But because this can be a constraint depending on your machine, we also provide this option to set voxel-wise to true. And here you compute your voxels independently. You don't get the benefit of vectorization, but you can parallelize this computation because each voxel is computed independently. But importantly, in this setting, you cannot apply total variation. So basically, you don't have Roomba, you have Umba when you set voxel-wise to true. And then we also have this use TV parameter. This determines whether you apply total variation. And once again, this is only possible when voxel-wise is set to false. Okay. Next, we have this fit method. So this is consistent across all local reconstruction classes in Dipy. You pass your data, an optional mask, and you get this Roomba fit object, which has all the information you need about your FODFs and your volume fractions that you can access. But before we get into what this Roomba fit object is and how you use it, I want to show just some code snippets of how you can parameterize the RUMBA-SD model. And all the code you'll see in this presentation is a simplification of the Roomba example that's on the Dipy website. So if after this talk you want to actually try running this code and interacting with Roomba directly, I would suggest checking out that example and running that notebook. But this is a streamlined, simplified version of the example that we'll go through together. So to start, we have to initialize our data parameters. So here we load in the Stanford-Hardy dataset in Dipy. This is a single shell dataset. We can initialize our gradient table GTab on line 8. We can then initialize our parameters about our scanner from lines 9 to 11. So we set our recon type to SMF. Here we set number of coils to 1, but like I said earlier, this is ignored in the SMF case. You can just leave this as the default value in the constructor. And we set our acceleration factor to 1 as well. Next, we have to set our response parameters. So first, we are identifying the sphere we want to use. So as I said earlier, it's advised generally to use a hemisphere because this halves your computation needs, and you get the same amount of information in the end. So here we're converting this 724-point sphere into a hemisphere, so we'll have a 362-point hemisphere that we're working with while fitting. Next, we set our gray matter response to none. This is because Stanford-Hardy is a single shell data set, and so there's no point in having both compartments. And then we set a CSF response to 3 to the negative 3, 3 times 10 to the negative 3. This is the default value in Roomba. And it generally will work pretty well for most use cases, but we show it explicitly here. Next, we have to extract our white matter response. So as I said earlier, there's 2 methods that Roomba lets you take for extracting this. One, you can get your tensor eigenvalues, and this is the auto response SSST method, which is in the CSDConv module. You just pass your gradient table in your data, and it extracts your tensor eigenvalues for you in this way, and you can pass the resulting vector directly into Roomba. You can also use this recursive response method. So this is getting that spherical harmonic representation I mentioned earlier. It essentially tries to isolate which voxels have a single peak and averages those signals together in a spherical harmonic representation. And you can pass either of these white matter response objects on either of these iterations of line 7 to Roomba directly, and they'll be used in the same way to construct that dictionary of rotated disks. Lastly, we have our optimization and fit parameters again. So here, lines 1 to 4, we just set what we want our optimization parameters to be. So 600, that's the default number, right, in Roomba. Here, because we want to use total variation, we set voxel-wise to false and use TV to true on lines 2 and 3. And we set verbose to true on line 4 because why not? And then we use all these, throw them into the Roomba constructor, get our model and call the fit method and get our Roomba fit object, which has all of the information that we need. And now we will go through that class now. I'm sorry if this is a bit dry, but we'll go through this systematically once more. So once again, we've grouped all of these attributes and methods into some functional partitions, and we'll go through these sequentially. So to begin, we have our core attributes. So when you get your Roomba fit object, you still have access to the model that generated the fit. So a RUMBA-SD model object. You still have access to the data that the fit was conducted upon in this data attribute. And then this model params attribute is where all of the information, all of the good stuff is stored. It stores the FODF and the gray matter and CSF volume fractions for each voxel. So in this example, we were using that 362-point hemisphere. This means that for each voxel, we'll have 364 points in this model params attribute. The first 362 will correspond to the FODF along these directions. Then the last 2 are your gray matter and CSF volume fractions, respectively. These vectors for each voxel are normalized after the computation finishes. So they sum to 1, and this is nice because you can directly interpret these values as being volume fractions. So if you have 0.2 in your gray matter slot in this F vector, then you can say, okay, 20%, or you can estimate that 20% of your voxel's volume is gray matter. So it's easily interpretable. That's a nice property of how Roomba does the fit. Now, you don't actually interact with this model params object directly. We provide all these attributes and methods to basically slice and dice this array. So first are our white matter slicers and dicers. There's this ODF method. It had to be a method for compatibility with the dipy structure, but it essentially behaves as an attribute in Rumba. You call it with no parameters, and this returns your white matter FODF for each voxel in an array. So with a 362 point hemisphere, this will have 362 dimensions for each voxel. Right? We also provide this FWM, which is the fraction of white matter attribute. This essentially just sums this ODF together and gives you some estimate of the total volume fraction in the voxel that is a result of white matter. Next, we have these isotropic compartment slicers and dicers. So we have FGM and FCSF. These get the gray matter and cerebrospinal fluid volume fractions respectively. So just getting at these last two components of these model params vectors for each voxel. And these correspond directly to the gray matter and CSF volume fractions within a given voxel. We also provide this F-iso, which is the total isotropic volume fraction for each voxel. And this is the sum of the gray matter and CSF components. And because of the normalization I mentioned earlier, if you add this F-iso to FWM for any voxel, this sums to 1 because of how model params is normalized. Lastly, there's some miscellaneous attributes and methods. So we have this combined ODF iso attribute. This essentially just, it distributes the isotropic volume fraction evenly across the entire ODF. And this is just useful if you want to visualize all of your compartments together, and I'll show what that looks like on the next slide. We also have this predict method, and this just predicts what the diffusion signal would be given the F and the H, so the dictionary and the FODF from the model fits. And because of how Rumba is, it's this dot product based thing. It just amounts to computing this dot product. So it's very simple under that. So now we can show this in action. So when you have your Rumba fit object from leaving off from the last code snippet you saw, it's very easy to extract all of this information as shown in lines 1 to 6 here. And then you can visualize these things in different ways. So on the left here, we show what it looks like when you just visualize the ODF alone. On the right, we show the visualization of this combined compartments thing I just talked about. You can see that when you combine them in these areas where there's lots of isotropic volume, you get these blue spheres. When you just look at the FODF, you get this like black void. So you can just decide for yourself which one you think looks prettier for your application. I also show here some heat maps of the white matter on the left and the isotropic volume fraction on the right. You can see, as I've emphasized, these two attributes are complementary, so they add to 1. And you can see this very clearly here in this snippet of the data we're working with. And also just a reminder, so the Stanford Hardy data set, this was a single shell data set. And so you cannot distinguish gray matter and CSF compartments. So when you have single shell data, I would stick to looking at just this F-iso isotropic volume fraction. The last thing I wanted to mention is we also used this Rumba dipy implementation in the Nikkei Disco Challenge 2021. Disco stands for Diffusion Simulated Connectivity Challenge. The challenge was estimating the connectivity of this phantom shown here with 16 regions of interest. So a bit of local reconstruction, a bit of tractography and streamline processing as well. We used a pretty straightforward pipeline, all contained within dipy. So just Rumba for local reconstruction, and then dipy's probabilistic tractography, as well as some streamlined thresholding afterwards. And we did not win this challenge by any means, but we achieved comparable performance with pipelines that were using very sophisticated tractography and streamlined processing methods. And so we're happy with this result, and we think it does show that the Rumba implementation in dipy is correct and that it's a powerful local reconstruction method. So just to some closing thoughts summary. So RUMBA is, R stands for robust, U stands for unbiased. It's robust because of total variation, spatial regularization, and the option to apply that to your local reconstruction problem. It's unbiased because it explicitly models the Rissian and non-central chi signal-dependent bias, so using that likelihood expression we showed earlier. It's a very flexible method, so it's compatible with single or multi-shell data. It's compatible with spherical or Cartesian acquisition schemes. It's also capable of accounting for partial volume effects, although remember, in single shell data, you can't distinguish the compartments. You can only combine them into one general isotropic compartment. And now we're very excited that it's available in Dipy 1.5.0 in the form of these two classes that I've already gone through. And we hope that you'll find RUMBA useful for your research, for your work. And yeah, if you have any questions, I'd be happy to address them now. Thank you, guys.